Afternoon. I'm Tom Gardner, a member of the Silicon Valley Technology History Committee and one of your presenters today. Our committee is part of the IEEE Silicon Valley section and dedicated to presenting events on significant technologies and products that originated in the Valley. You can learn more about us at www.siliconvalleyhistory.com. We have 4 speakers today. Each will briefly describe their background and then share their personal observations on the history of storage interfaces. We will all participate in a panel session to answer any questions you might have. Personally, I've spent most of my career in the storage industry, starting with interfacing OEM and PCM disk drives and systems at Memorex. At Shugart, I was responsible for SCSI, and later at Auspex, I worked on NAS systems. I was an early proponent of iSCSI. Lately, I've taken an interest in most aspects of storage history. In the beginning, at least if you think of a von Neumann architecture as the beginning, there was just memory. Data and program were inputted into the memory, the machine ran, and results were outputted to a medium. Since then, we've been on a search for unobtainium. Unobtainium. There's never enough memory. And it's never small enough, cheap enough, nor fast enough to be located right next to and directly addressed by the CPU. Absent such a memory, we developed layers of memory and storage being slow memory. Maybe the first 5-layer system was the IBM 650. In order, a core buffer, a drum as main memory, disk storage as secondary storage, and tape storage as tertiary storage. On the right, depicted as a modern memory and storage triangle. Not that anyone looked at it like that then. Each layer was a different technology, having a different cost and different performance. Each layer has an interface. In the 650 days, they were all custom interfaces. And every time IBM tried to put a RAM hack on another system, they had to design a new interface. Not a very efficient way to build systems. Here's a modern hierarchy in 8 layers. Towards the top, they resemble memory interfaces, and towards the bottom, they look like network interfaces. In my experience, the layers are not contiguous, as illustrated here, and have gaps in cost and performance, with cost gaps almost at least four times larger, justifying at times huge performance gap. There's almost a quantum effect. It's not worth the pain of an interface unless the gap is big enough, which is why most gap-filling technologies have failed over the years. As an aside, I attended a storage conference recently where a cloud storage vendor offered several layers of storage, each precisely separated by a 4-to-1 price per unit of storage. I'm sure they did not correspond to what he had physically installed. He was just metering the maximum money you could get out of the market. I'll start with JBODs and their dumb drive interfaces. Now, that's a bit pejorative. It's because the later on interfaces were called intelligent. They really weren't very dumb. In fact, they were really hard to implement. 2 examples. On the left, IBM 2314 drives and a 2314 control unit, and IBM 2401 tape drives and its 2403 tape control unit. On the right, a CDC installation at Lawrence Research Livermore in the early 70s, 22 disk drives, about 2.2 gigabytes. They were the CDC 3BR XX series. Ripping apart the triangle and showing the interfaces, typical of the 70s, really going into the 80s and 90s, we have a memory bus to which the register and the main memory connect. And on the left was a typical mini construction where you have a controller which plugged in the memory bus and presented the so-called dumb drive interface to secondary storage and tertiary storage. On the right, typical of the mainframe, plugged into the memory bus was a channel. Arguably, today we'd call it a South Bridge. It presented somewhat of a standard interface to a control unit, which then implemented the dumb device interface to the tiers of storage below it. Here's a picture of an SMD interface, the physical aspects from the mid-70s. You typically have 3 cables, a power, which I'm not going to talk about, and a control and data cable. The control was daisy-chained and provided a number of functions like selection, movement, status, starting and stopping, and power control. Data was typically unidirectional and had signaling for synchronization and safety. Tape was a little different. Their data cables were 9, 7, 9, and 18 bits wide and analog in nature. Here are some of the significant dumb disk drive interfaces, really from when they first came into existence as standard, in my opinion, around 1969 with the DEC RPOX series. I think this was the first time you could actually buy a disk drive with the same interface from multiple vendors like Memorex and Calcomp and Ampex, and I think about 6 or 7 vendors produced that product. They were dumb because there was a lot of drive-specific functions in the controller. Serializing and deserializing, error correction or error detection, or both, generation and then detection and correction if in fact there's an error, turning the series of good customer data into blocks and then unblocking it, and then encoding it while writing, and one of the harder parts, data separation, but not the hardest part. This was a barrier to technical innovation. In my experience, it could delay the innovation of a new high density or higher aerial density by 2 years or so, because it was really hard to do. Now, CDC did move the data separation from the controller to the drive in its SMD interface, but they still had a 2-year hiatus from the time they shipped the product until the time they saw significant volumes. The problem was obvious to everybody, and that led to the movement to intelligent drive interfaces, parallel intelligent drive interfaces. Probably it was first recognized by IBM around 1972 when they ripped their control unit apart, took the 3830, made it a Mod 2, which had no drive functions, and put all the drive functions in a box, which they bolted to the side of a 3330. This is a picture of the DEC equivalent mass bus box, about half the size of a dishwasher, which it bolted to ISS drives. And then, thank you, Moore's Law's, things shrunk. We had sort of a standard with SASE and SCSI first in bridge controllers. And then we moved on by the 90s to standardized SCSI and ATA, which were now chips on a board. From a current perspective, the interfaces look like this. We have an upper bridge, which talks to main memory and secondary memory. On the chip, there are the registers and a bunch of caches. And then we have a lower bridge, which provides a variety of interfaces. Early on, it was intelligent parallel interfaces, and now it's pretty much all intelligent serial interfaces that then talk to all of the storage, secondary, nearline, and tertiary. Moving on to parallel interfaces, really began around 1979 when Shugart Associates published their SASE paper, and Shugart Associates, along with NCR, went to ANSI to start the standardizing process. On my right is a Fujitsu bridge board interfacing to an 8-inch drive, and you can see the bridge talks to SCSI on one side, and the other side bridges through dumb disk drive interfaces to either disk or tape. Xebec was probably the first company to produce an integrated, embedded SASE or SCSI really in 1984, but there were problems. The problems were the specifications were pretty general. There were lots of choices, and you really couldn't put together a system unless all of the chips were from one or some closely associated vendors. This sort of got solved between 86 and 1990, first by coming out with the common command set, and then by creating common software interfaces. Also in this time period, we started seeing the technical committees that were writing the interfaces separate from the marketing organizations that were promoting and teaching how to use the interfaces. For example, SCSI Trade Association and SCSI Forum, both were formed around 1984. They were separate and distinct from the ANSI committee that was documenting the actual specification. But by 1994, the world was SCSI, and a newcomer, also a parallel interface of the parallel ATA. But there was one more innovation, I think, in SCSI, and that was the making it into a layered interface, separating the commands from the fabric. Here, we see 3 layers. This concept actually comes out of IPI, which was originally also a 3-layer definition, and was adopted by SCSI in 1995. Here's a summary of the evolution of parallel SCSI. SCSI introduced logical block addressing, which is one of the key breakaways from the physical device addressing that was one of the impediments in the dumb disk drive interfaces. It went from a lot of bytes to an awful lot of bytes. It went from limited devices to a lot of devices, from a relatively simple command set to a very complex command set. I counted them, 62 pages here, 440. And it didn't do so well in the signaling end because sending parallel signals over long distance is really hard. And it started at 6 meters for single-ended cable and 25 meters of differential, and it wound up in its last embodiment with only low voltage differential out to 10 meters with 8 different connectors. Now, also in the 90s, we started seeing parallel ATA. Parallel ATA really was a Western Digital concept that they convinced Compaq to adopt. And in 1986, Compaq shipped in its Portable 2, really the first parallel ATA, no name at that time, a Western Digital controller bolted to a mini scribe drive. It became embedded and public with Connor in the CP342 around 1987. The shout out here probably goes to Ken Hallam of Western Digital and Ralph Perry of Compaq. Ken for promulgating the idea and Ralph for adopting it. And in one of the great mistakes in storage history, control data was given the opportunity by Compaq to do their 3.5-inch ATA drive. They declined it, and that's how Connor wound up doing it. Connor actually published the first task file interface specification, as they call it, which didn't get to the ANSI committee until 1989. Here's a picture from some of their literature. LBAs were included, but really not supported by any software. So we have the physical problems in the interface with this was a cylinder head sector physical interface. It got presented in '89, but it didn't get published until 1984. At that time, LBA was added, but really not used. It was 35 commands, and it used either programmed I/O or direct DMA I/O up to 8.3 megabytes per second. The next 2 years, there were wars by the vendors that had tried to establish their versions as a standard, and ATA2 actually implemented most of the standards as standards. The big change was ATA4 in 1988, which basically transported SCSI across the ATA interface. It was a packet interface, more commands, higher speed. And then by ATA6, 2002, it became obsolete, and that was the last parallel interface. So this century is a serial century. The world turned serial. Actually, it started first in 1981 with digital equipment and their storage interconnect and the RA80 disk drive. But no one followed DEC. The world went then serially in systems, again, DEC leading with its computer interconnect, then fiber channel, and then IBM and ESCON. But we started seeing in the device world with first SATA. The spec started in 2000 and then got published by 2003. That's sort of the methodology I use here. As far as I can tell, parallel interface drives ceased being manufactured sometime between 2011 and 2014. So if anybody here has any better dates, I really would appreciate them. Finally, a quick view of system progression over this time period. Well into the 80s, it was JBODs. But by now, we have a universal server, almost any protocol, over almost any fabric. That's an EMC Dell PowerMax 8000 on the right. In my opinion, there were 6 technologies that happened along the way, and not, in my opinion, one not so important paper. The 6 technologies were mirroring, first by DEC, and then virtualization and distributed parity, probably first by Array Technology. Auspex introduced NAS. EMC came along with emulated CKD. And then EMC put a NAS head on a SAN server, and IBM brought us iSCSI. Now, the RAID paper did give us a poor taxonomy, but as near as I could tell, the industry started before the paper grew, and grew substantially for quite a while before the term got adopted. EMC, for example, by 1985 was the industry leader, exceeding IBM in the mainframe market share without ever using the RAID word. They called it arrays. I do give the Berkeley crew credit for hosting a series of meetings in the late 80s and early 90s on arrays, attended by academics and industry participants. I'm certain the exchange at those meetings helped grow the industry far more than the R word. So here we are in 2021. I'm certain SATA will be around for quite some time. I still think the world belongs to Ethernet, and I'm really looking forward to seeing wins out which protocol over which fabric. Our next presenter is Grant Saviers.
Okay. Well, thanks, Tom. So I'm going to try and put a little taxonomy around the evolution of storage interfaces into several major buckets. My background is degree in computing before there were computing science degrees, 24 years at DEC, of which 22 years were spent building the storage organization in a multi-billion-dollar organization, and 2 years running PCs. And then I was recruited to run Adaptec and be the SCSI king for a while. Subsequent to Adaptec, I invested in public and private companies and on boards. And along the way, I've been a trustee of the Computer History Museum since its inception, and sponsored the storage special interest group at the museum. So one of the questions which evolves is, what storage interfaces are we talking about? And Tom gave us a lot of detail there. But the questions are, where are the real-time control and data functions? How much technology dependency is there? Where is direct memory access done? There's a lot of philosophical issues about that, and ownership ones as well. How error detection and recovery is done, and sometimes, as Tom mentioned, it's really competent. It requires a high degree of competence, and it's very complex. And finally, in the large systems world anyway, reliability, availability, and serviceability and failure prediction were quite critical in building subsystems. What wires and protocols at various levels, were they architected, multi-generation, or ad hoc and de jure? And finally, what did the operating system driver and how did it interface to the controller or channel? Logical to physical mapping, of course, in the beginning, it was all physical access. Now it's primarily logical. How was error recovery handled, and what performance optimization? It's also interesting that different users or different applications had different requirements. The transaction processing and database systems guys love to hack bits rather than work with a file system. So there was some differences there in how things worked. So my view of the generations is logic cost drove a lot of the first generation. And cost, not only in the sense of the dollars, but cost in terms of reliability. And IBM, I think, was a genius at dividing up the prints for a subsystem into maximum reliability. Fire hose cables, coaxial cables, and the central processors were dedicated to doing the I/O. In generation 2, we really transitioned into the disk world with larger disks on big systems, and the needs for fan out and distance to put those big systems that you saw in Tom's picture really drove a lot of the architecture. So storage controllers became separate, and then they were modified to have strings and channels to kind of expand the fan out. And you look at the implementation technology before in generations 1 and 2, they were really sequential logic and state machines, and subsequently to generation 2, we are driven by microprocessors and ASICs. In generation 3, we really started to migrate into technology independent bus and protocols, and primarily that means we got away from understanding the magnetic recording bits and nanoseconds in the controllers. They delegated that back to the disk drive, and that enabled multi-generation subsystem, both hardware and software architectures. And generation 4, which is the last generation I really participated in, was building intelligent controllers and being dominated by serial interconnects. So when we look at the first generation, I love to look at the IBM 1401 as a canonical and incredibly important computer. More than half the computers in the world were 1401s at one time, and the 729 tape drive. So that machine was totally dedicated to doing I/O when you wanted to do an I/O. The CPU ALU managed everything. The programming stopped. There was one exception prior to the 1401 and the early 700 series IBM systems, which was the UNIVAC 1, which had fully overlapped I/O. They're kind of a genius architecture of the time. Now, the interesting thing was analog read signals were passed directly into the central processing unit. Always a little adventure if you're into bits and nanoseconds over wires. Coaxial cable bus was really fire hose size cable, literally. You could have eight tape drives on the daisy chain. They put analog read signals into the same cable, and all those analog signals were processed in the CPU, and it was in a box called the TAU tape adapter unit. And the huge connector, you can see a picture of it here on the right, about 6 inches square and weighed 10 pounds. So there's a milestone in connector technology. The architecture of the bus for the 729s survived 6 generations of 729s over the years, all the way to the beginning of the System 360. In generation 2, disk drives really start driving changes in the architecture. And this is true across the 2311, 2314, 3330, Winchester, and their clones of those products. Picture here is 2314 storage facility, 8 drives online, a spare, interesting choice by IBM, and its large controller. So these are often interface designs of the day per drive, per size, per technology. And frequently, the market leader in a particular size segment would set the standard. IBM clearly did for large disk drives. Diablo for the Model 31 set a standard. Control Data for the SMD. So that's kind of how any notion of a standard or a multi-source product could become available with all the same technology. All the motion control functions moved into the disk drive, and overlap seeks were possible. So that was performance enhancement. Peak detectors usually migrated back into the device, so there was some areal density, magnetic recording independence. But as Tom mentioned, it became very difficult for system manufacturers to learn the nuances of data recovery and phase lock loops and encoding systems from controller technology to controller technology. So buses remained single-ended daisy chain buses, and string controllers emerged to prevent large fan-outs of dozens of drives with simultaneous data paths. In the generation 3, we start to move technology-independent buses, and DEC tried something rather unique with something called the mass bus, based out of necessity, a huge matrix of complexity of operating systems and CPU architectures. Gordon Bell decided, he was the VP of engineering, that we needed something to solve that problem. And the mass bus was invented, which allowed tape, disk, and bulk RAM on a single storage bus. The bus enabled any mix per controller, multiple generations of technology, multiple generations of disk drives, all kind of the large format, spinning, removable and fixed and Winchester drives. Again, a standard 8 devices with something new happening, parity on data and control in terms of the interface between the drive and the control unit. And was one controller per CPU in terms of how it was done, maybe multiples. Customers loved it because they could just plug in the next generation and go with a new technology while preserving their old and easily migrating that older storage data into the new technology. The DEC mass bus, as I said, moved all the magnetic recording technology into the disk drive. And the IBM plug compatible manufacturers, who DEC at that time bought those large disk drives from, modified to the DEC specifications. And DEC engineered a large bustle that was bolted to the side of the drive to provide that serial to data, parallel data conversion in the bus interface. Fortunately, DEC never went with count key data like IBM did to maintain tape compatibility. But we were always fixed block architecture going all the way back to the early DEC tape. So dual port drives were the standard for redundancy and performance. That bus had a capability of one data transfer at a time, but overlap control. And tapes were implemented in a slightly different way with a head of string controller to manage the various tape technologies. And that maintained a de jure interface at the device with the mass bus head of string control. There were 2 devices that actually integrated the mass bus electronics directly into the drive, the DEC's last head per track drive and the 3350. I couldn't resist not showing this picture, the washing machine size of disk drives. This is a ISS disk drive, I believe, that DEC bought and added to the mass bus. So here's compared to the washing machine next door. And to give you a perspective of history here, a 240 volt 3-phase, 3 to 5 horsepower motor, 10,000 or 2,500 watts, 40 megabytes and 25 millisecond access time. And now what you can get for $40 a 1 terabyte drive that's a half a watt and has a 200 microsecond access time. Technology has changed a bit. Generation 4, intelligence and serial comes in. DEC migrates from mass bus into digital storage architecture and clustering. The whole goals are really performance and reliability and large data systems, data integrity. The serial interconnects became feasible because silicon became cheaper than copper and the performance was there. Radio connections to devices enabled very small cables and connectors for higher fan ends. And interestingly enough, this technology was transformer coupled. So multi-floor, multi-power source, and infinite ESD protection was possible. This was very interesting. The DSA came about 1981 as multi-tech and multi-generation and high performance. Disks were perfect logical block devices like SSD is now. So the disk drive actually mapped the physical to logical and revectored bad blocks into spare space. There was spare space on the disk for housekeeping to do that, and error logs and diagnostics, a very small data loss in order to implement it. And interesting to see that it was 15 years later that this became something more in the mainstream. There was a robust architectural definition of the mass storage control protocol. The architecture was really CPU independent, and we did maximum performance optimization in the primary large system controller, which was the HSC, or hierarchical storage controller. It was envisioned and actually implemented over time to have 5 levels of storage in the control unit: cache for the disk drive itself, tape, bulk RAM, and tape libraries. And all were connected over time to the HSC family. Performance, it offered a lot of interesting things: N-way mirroring, auto restore, rebuild and catch up, online mirroring, full real-time diagnostics, multi-levels of I/O performance optimization. It could put 56 devices on an HSC and have multiple HSCs per cluster. I think at the ultimate implementation, a cluster could have 24 devices, which were a mix of VAXs and HSCs. So you could have a pretty large storage family and envelope there. And multiple simultaneous data paths because of the radio connections were possible. And interesting, later in the last generation of the HSC, it incorporated SCSI interfaces to adopt industry standard devices. There are many storage generations at all levels of the hierarchy in terms of the disk and tape capabilities and tape libraries. And there are also simpler controllers built that didn't have this level of optimization and RAS functionality that were built for the Unibus, the QBus, and BI bus DEX systems. One of the questions which, I'm going to SCSI, and Tom has talked about that quite a bit. As he had noted, it's somewhat technology independent. One of the things that was always difficult in terms of adopting SCSI into large systems was very limited RAS features and connector proliferation that drove everybody crazy. Of course, it went through many generations of bus width, bus data rate, and bus signaling technology. It evolved over time from programmed I/O to DMA, and as I mentioned, the actual bits and nanoseconds of the bus signaling did change. As it evolved, of course, there was an architectural melding of various ideas. To probably some extent, the DEX storage interconnect influenced this a bit, and we evolved a bit from dumb bits and blocks into some server grade products. Currently, I think primarily for the data mining world, and very large MTBFs. So with that, there's also one question that I was asked back in 1983 by Gordon Bell, like, why weren't you putting the file system in a disk drive? The politics at DEC prohibited that, but OSPEX came along, and then network appliance, and now the cloud is perfect file storage. And of course, there's SATA proliferation, as Tom covered. Many RAID flavors, and DEC did sponsor the research at Berkeley. It was fascinating to do that. But I would say, why RAID now when redundancy in the cloud and mirroring are so cheap? And now, if some RAID systems fail, for other reasons than the disk drive failure, you're kind of got a problem in terms of how you're going to recover that data. So there's some issues there still to work on. So I'd now like to introduce Jay, who's going to talk about the evolution of block storage system interfaces. Jay?
Thank you, Grant. Good afternoon, everyone. I want to talk to you about the evolution of storage system interfaces, not so much at the device level, but at the storage system, storage controller, whatever your favorite word is for that. I have spent most of my career in building storage systems of various flavors. I worked with the guys at Berkeley on RAID during the early part of my career. I worked on mainframe storage systems, ended up as an IBM fellow and chief CTO for IBM server storage and networking businesses before I left to take the same role at Dell for a few years. And I'm still, and since then I joined a startup that's working on currently what I think is the world's fastest storage system, doing 15 million IOPS. So I'm still doing storage. So I've been around for a while, still doing it. So what I'd like to do is start with the IBM mainframe block storage system interfaces, and then move my way on to the more industry standard part of the world, the servers and the block storage system interfaces thereof. And this is a 15-minute talk. There's no way I'm going to be able to cover everything. So, even though I have built clustered file systems, no talk on file, no talk on object, no talk on tape. So with that caveat, let's begin. So I'm going to begin about 20 years before I actually joined IBM, back in 1964, with the IBM System 360, was the introduction of count key data. And count key data was really refers both to the format on the disk and the way you spoke to the control unit and the disks with these channel command words. As you can see in the picture, the mainframes had channels. You could kind of think of them as host bus adapters today, I suppose. They connected to the control unit with these, parallel bus and tag interfaces that maybe went 100 feet or 200 feet. And then you had the control unit that then talked to count key data disks. You can see at the bottom that the records had count field, an optional key field, and a data field. And all of these could be variable length. And the idea was that the mainframe processor and memory was too expensive to be doing this kind of searching. So that was sort of offloaded to the channel and the control unit. An interesting thing about the way this thing worked is that if you look at the gaps between the count field and the key field, or the key field and the data field, a lot of work had to happen in that gap. You had to read, for example, in the channel program I show you in the middle there, where you are searching for a particular key, that key had to be read, moved all the way up to the channel through the control unit. The channel did the match. And if the thing actually matched, then you had to send another command down in the time between that inter-record gap, or between the key and the data field, to say, go read the data field. So what happened over time is that as track density increased and disks spun faster, more and more of the space was just lost in those gaps. And that was one problem that IBM faced. The other problem, of course, was that, each count key data disk was unique and proprietary, and it took $100 million to develop each new generation of count key data disk. So the writing was sort of on the wall that there really was, it was really important to move to where the industry was with fixed block disks, both because of lost gaps and because we were spending $100 million every time we needed to build a new one of these things instead of riding the industry wave. So two things happened. One was CKD emulation. Tom talked about this in his overview. I was personally involved in doing CKD emulation. And so the idea was that you'll see in the yellow, the physical track was fixed block disks, fixed block sectors, and then you took those count-key data fields and then you packed them into these fixed blocks. And there were two key problems, really, perhaps more, but I'm going back in time now, but clearly performance was going to be a challenge. For example, anytime you needed, for example, in this picture, say data 2, shown on the third fixed block sector, anytime you change that, you would have to first read all of that sector, change the part that needed to be changed, and then you had to write it back. So there was sort of a read, modify, write kind of problem. Very similar to read, modify, write with RAID. You could kind of solve in somewhat similar ways, but there was also some techniques like the predictive track table that was used to solve some of these kind of problems. There was also ways in which you would pack these count-key data fields and leave the actual gaps in the mapping so that the set sector command, which told you how far to rotate on the track, could be preserved in the mapping, and you didn't always have to read stuff from the beginning of the track. So performance was an issue. Reliability was also an interesting issue, because anytime you change something in the CKD world, in the pure CKD world, you could change a record and not have to modify the record before it or the record after it. But with this packing inside fixed blocks, when you changed a record, you really had to rewrite the parts before it and the parts after it, even though the channel program never asked you to touch that stuff. So you had to be very, very careful how you did it. Otherwise, you ended up with new failure modes that never existed in CKD. But nonetheless, all this worked. And interestingly enough, we still do count-key data emulation to this day. MVS never changed, to support fixed block commands. It still supports CKD and extended CKD commands. And the emulation itself was done in two different ways. One was you emulate all this stuff in the channel to control unit interface, the top part of the picture, and you just make it all look like CKD. Or you could also emulate stuff down at the disk level, and you could take a bunch of fixed block disks and make it look like a CKD disk. Then the control unit didn't have to change any code. The channels didn't have to change any code. So history here, the first CKD emulation was done on what was called the baby mainframe in those days, the 9370. It was done in 1987, and I was personally involved in doing that. The EMC approach, which Tom alluded to, came a few years later in 1990. And then later in 1994, IBM did the RAMAC array. That was where they actually emulated. They took four 3.5-inch Starlight drives and made it look like a 3390 count-key data disk. And then the control unit didn't have to change. You could just use the standard 3880 or 3990 control unit. So very interesting history here. Moving on to the other approach that IBM took to sort of solve some of the problems with CKD was an approach called extended count-key data, or ECKD. By the way, both CKD emulation and ECKD became possible once microprocessors became cheaper. You could start putting, beefier processors and more memory into these control units. You could do things like caching and non-volatile storage. And ECKD was a way to change what was purely a synchronous operation, as I described to you, into somewhat asynchronous operation. So the search key loop was replaced with a locate command, and you could send the data, you could send the locate command to the control unit, and then the control unit would disconnect from the channel. It would find the appropriate piece of data, and then the read or write operation could happen after the control unit reconnected, after it had located the right piece of data. So this happened in the 1985 timeframe with the 3880 control unit. But, access methods still continue to use, I believe, CKD even to this day. So even though ECKD came along, you really end up having to support both ECKD and CKD. Like I said, we still do CKD emulation on mainframes. Now, all of that was using the bus and tag cables that I mentioned. You know, these were gray cables and blue cables, as I recall, in those days, that went hundreds of feet. And then, of course, ESCON came along. We moved from parallel to serial. Now we went all the way up to 10 megabytes a second. The bus and tag cables stopped around 3.5 megabytes a second, allowed greater distance, switching, and control units could now talk to multiple mainframes at the same time. By this time, as you can notice, I mean, I no longer have CKD disks in this picture. It's all industry standard fixed block disks, and emulation is just standard fare now inside these control units. But you know, the MVS operating system never really changed to move to fixed block. After that, you know, the IBM world moved to FICON, which is really eCKD or CKD commands on top of fiber channel. So this is one more example of IBM saying, look, let's ride the industry wave. Just like they moved from CKD to fixed block, they moved from ESCON to just let's use fiber channel and let's do FICON. And now, of course, things went faster and distances moved up to 100 kilometers. And then later in 2009, high performance FICON came along. This is just one more example of leveraging what was already happening in the industry to make things better, to ride where the energy was going. So FICON adopted the FCP style of how commands, data, and status would be transferred, and that speeded up things a lot. You needed fewer channels to get the same performance. Next, really the last, you know, my story ends with the DS89 controller of today. This is the mainframe of today, the Z15 server. It still has channels. It still does FICON. It still does high performance FICON, still does CKD emulation. We still emulate the 3390 CKD disk, which went out of business way back in 1993. Kind of amazing how all that happens. The one new thing that was introduced back in 2017 was something called the Z hyperlink. This again is another example of writing things that are happening in other places. PCIe was happening, and this is sort of a point-to-point extension of the PCIe bus, like a retimer card, and it allows very high performance. As long as the control unit is within 150 meters, you can get 18 microseconds of response time. And that's pretty much where the mainframe story ends. And I want to pick up on the industry standard server side of the world, beginning with fiber channel. And really the first fiber channel controller, SCSI commands on top of fiber channel, was the Sun Spark storage array back in March of 1994. Really interesting to look at some of these numbers. You know, 31.5 gigabytes in a box. Now we're talking hundreds of terabytes and petabytes in a storage box. You know, the box I'm building now is a 2U box with 200 terabytes of all flash. Look at the performance, 2000 IOPS. Now we're doing, you know, 15 million IOPS, 3 orders of magnitude and more, $1.62 a megabyte. Now with all flash arrays, you can get it for under $1 a gigabyte, right? Again, factors of more than 1,000. So that was SCSI. The next thing that came along was iSCSI, and that I want to talk about. There's so many things. It's just hard to talk about all this stuff in 15 minutes. But I do want to talk about iSCSI. Again, my team was involved. We actually built the first prototype back in 1998. A lot of discussions about, hey, should it be Ethernet? Should it be IP on Ethernet? Should it be TCP IP on Ethernet? Of course, we ended up TCP IP on Ethernet. The first draft was submitted to the IETF back in 2000. It got ratified in 2003. Of course, we all know lower performance than fiber channel, but it had the advantage of running on customers' existing network infrastructures. And by the way, I mean, the first iSCSI storage product was really in 2001, was the IBM Total Storage IP Storage 2200i. As far as I know, it's the earliest iSCSI product in the industry. And I know we worked on the first iSCSI prototype back in 1998. Actually, we met with Andy Bechtolsheim. I actually brought him to the IBM Research Lab and showed him a prototype of iSCSI working. And he said, good, let's go do a draft of this thing together. That's how the first draft came out, the IBM SCSI, IBM Cisco IETF draft, which also included our IBM colleagues in Haifa and some people that were on my team. And I'm going to, the last thing here is, of course, NVMe. So now we're talking about a new standard that emerged recently to go after high-speed SSD storage. The NVMe over PCIe is for talking to local SSDs, but again, my focus is on storage systems. So that was extended to go over 3 different transports to become NVMe over Fabric. And there's 3 possibilities. You can do NVMe over TCP, you can do NVMe over Fiber Channel, you can do NVMe over RDMA, and within that, you can do InfiniBand, RoCE, or iWarp. Very high performance, much lower complexity. There's no notions of tracks and sectors and all this blocks and all this stuff that's still there in some of the SCSI stuff. And we have examples of products that started to roll out. First one I'm aware of came from Pure Storage that did NVMe over RoCE in 2019. And there's 2 examples of people that built NVMe over TCP storage boxes in the 2020 timeframe, both Fungible and Lightbit Labs. There may be others. I'll end with this one chart because it really shows you how much we have come in interfaces. And this is just comparing the NVMe over TCP interface to the iSCSI interface, the thing that just preceded it. And what you see here is some performance measurements taken jointly by folks from Intel and folks from Facebook. What you see on the left side is latency. You can see that the latency of NVMe over TCP is very close to having local SSDs. So, you're going over a network, you're going over TCP, you're going to a remote controller with SSDs, and yet the latency is so close to that of having local stuff. It's about 1/10 that of iSCSI. And on the right side, you can see the throughput, and very similarly, the throughput of NVMe over TCP is about 10 times better than iSCSI, and very, very close to just having local SSDs. So it's phenomenal how far we've come with these interfaces. And with that, I am going to turn it over to our next speaker, Amber Huffman, and she's going to talk to you about fast and efficient interfaces for the SSD era. Amber, over to you.
Thank you, Jay. Really appreciate the introduction and the invite to speak to everybody today. So let me share my desktop. So I'm really excited to talk to all of you today about fast and efficient interfaces for the SSD era, and I'm really going to focus on NVMe technology. So I co-founded NVMe and continue as president of NVMe to this day. So sticking with it. So the first, you saw some of these charts earlier of memory and storage hierarchy gaps that we've had over time. And so one of the things that we've been doing with NVMe, and I go back to when I first started at Intel, one of the first projects I worked on was serial ATA development with Knut Grimsrud. So building upon where we went with serial ATA and really optimizing what we could do with hard drives, how do we enable the era of SSD storage? And the group that I was part of at Intel is the group that have found the Intel SSD business. And so how did we enable breakthroughs and make sure that as you got faster, both non-volatile memory, if we think about making NAND work for SSDs, but then as we got to storage class type of memories, how do we enable an interface that could really scale? And so this was what was in mind as we looked at NVMe. So this is a different way of looking at that same chart, which I think is sometimes a little easier to understand. So it's showing bandwidth on the y-axis, and it's showing capacity on the x-axis. And what it's really showing you is we have a bit of a chasm going on between what it looks like for memory with DRAM versus where 3D NAND flash and hard drives are at. And so how do we go address that gap and really provide the absolute best performance we can and really scale as we move beyond interfaces that were originally designed for hard drives. So with NVMe, I'll show you a bit of, kind of growing up to kind of go from a small consortia to a bigger lion or whatnot, if we use that analogy. So the first thing, if we go back to 2010 or 2009 when we first started, was how do we unify PCIe SSDs? Then we moved on to then how do we scale over fabrics, which Jay did a great job of mentioning. And then how do we just enable innovation as we continue to scale if we look at the history of how this will just continue to evolve over time. So our first challenge was why did we need a new interface? So I was very involved in serial ATA, parallel ATA, and some of the very first thing I worked on at Intel was how do we make 1394 work for storage? And so that obviously didn't work. And one of the challenges in a broad-based sense in terms of replacing parallel ATA. So a key thing was how do we really bring together the need for a new standard interface and crossing the chasm of adoption to get there. So I had fun as part of preparing for this talk to go back to old slide decks from 2009 and 2010 and whatnot. And so that's what you see here is really just understanding that PCI SSDs, if we think about Smart Modular and Texas Memory Systems and Fusion IO and those companies of about 10 years ago, and they were bringing out PCIe SSDs. And so how did we bring about really adopting a standard interface from the ground up? So what we did is, first off, it's always critical when at least when I've started an effort, is to have a horrible name. So we called it NVMe-HCI, so NVM Host Controller Interface, and then basically said, how do we do it for enabling it for enterprise? So we called it Enterprise NVMe-HCI, so that was really terrible. So we end up with a better name picked in the end. What you can see is the first thing we did back in 2009, 2010 is pull together critical people and really how do we develop a consortia that can go forward and really develop NVMe in a way that people will adopt. So if we go back to that time in history, it was really at the time, Peter Anufric was at IDT at the time. He joined me and really co-edited and drove the specification, and Peter leads the technical team to this day. And then we also had both Dell and Microsoft and several others on this screen as critical companies that worked with us. If you guys recall, Sandforce, for example, at the time, very much moving forward before they got acquired by LSI and so on. So we moved forward. Then we completed the specification back in 2011, and we moved into what we were hoping were going to be product introductions in 2012. One of the things we also did is we moved to forming a promoter group that exists to this day of what leads NVMe in the industry and trying to drive what makes sense and the best for the organization and for the industry. Now, one of the challenges we had at that time was we actually had a competitive challenge with SCSI Express was formed around the same time of proposing of how do we scale out SCSI over PCI-Express. So one of the key challenges we had was how do we take a look at what's worth the adoption curve? Because whether we talk about one of the key challenges of NVMe Express versus SCSI Express would allow you to basically carry forward that SCSI investment in infrastructure. However, your challenge as we look at the industry moving forward for storage class memory type of devices is how does it scale? And so what we found is in our experiments is really to get to breakthrough IOP performance, as well as both local and remote, like Jay was talking about, you really needed to get to where you don't require firmware being involved, where you have that ability to scale out to many queues, many commands, and have that parallelism and get things very optimized. So what you can see on the right-hand side is, for example, we were doing prototypes showing that basically we get to more than 1 million IOPS on, a few cores worth of work versus what it would take. And you'd have to go more of a 6 microsecond versus a 2.8 microsecond in traditional. So just how do we really get this performance without taxing the host CPU in a way that won't scale? So then another piece of how did we move forward in the industry with a brand new interface is also think about how do you bring forward the SSD era, both in form factors as well. So if we think about first, one of the things we had to do was the SSD form factor. So how did we go about creating hot plug connectors and other things. So that's a key thing of what we did on the 2.5-inch form factor. But then another thing that we saw around that time, I found a slide from 2011 of, hey, rather than M-SATA as a form factor, what if this is the first inkling of M.2, when we were first introducing the M.2 form factor and defining that for the industry for both wireless as well as for SSDs that we've come to know today. And so really optimizing for Z height and how we move forward when we were talking about, if you remember, the thin and light laptops, Ultrabooks, all of that type of thing was happening. Another key differentiator to make sure we move forward in the industry and actually had a successful transition of what we've seen in the past is the software enablement. We really have to get to where we have that software in the industry and have that software available. So a key thing was getting reference drivers for all the key OSs out there in the industry. So if we think about Linux, Windows, VMware, Solaris, UEFI, we were doing all of that plumbing so that that would allow industry adoption to start, because that was one of the major challenges is, do people have the inbox driver or not? Do they have to load a driver? Do they have boot support? All of those kind of things were critical to allowing us to move forward. And then a lot of why is it important to cross the chasm and really move forward with a brand new interface is showing what's possible. And so this is an example of back in 2012, EMC showing what was possible of designing with the right pieces. How could they get multi-core parallelism and building, a different type of storage platform and getting that performance. So that allowed us then to, over the course of the next year, just continue to move forward with a number of industry players. So for example, here was a major turning point as well, was Microsoft showing their storage grade, enterprise grade support for NVMe-Express and showing the latency and the benefits of what they got, especially in relation to SATA. So on this chart here, they're showing just how they got such better latency on NVMe, whether it was a flash versus a SAS SSD or a SATA SSD. So just how do we get to that ultimate performance and chase after that opportunity? And then what we saw is just continuing to move forward and really having that, evangelization, that vision. We went from 2011, where we delivered the spec, to then where we really finally started to have our first Plug Fest in May of 2013 and our first real deployments towards the end of 2013, but really more into 2014. So it was kind of that, hey, hurry up and wait, here's NVMe-Express coming. And so a lot of it was just sticking through that perseverance and just trying to build that community. So showing, and that's why I grabbed, one of the examples of the communities at some of our shows, whether it was Intel Developer Forum or Flash Memory Summit or other venues that we get together, how to show the industry coalescing around this interface to make it a long-term investment, because that's what people really need to see is this amount of change requires us having that long-term plan. And so then we just evangelized the value proposition. This just shows more early value proposition that we were doing, showing about the best-in-class IOPS, also showing the efficiency in terms of relative efficiency. If we look at performance, all of those pieces, clocks per IO and relative efficiency. So if I look then at what did we do on NVMe for the first step of our journey, we basically went from some of the gaps. We really enabled performance storage and secondary storage, and also, in other ways outside of NVMe-Express, persistent memory got introduced. So we really closed a lot of those gaps and enabled a much better tiering and hierarchy in storage and memory for all of us to enjoy the benefits of both NAND as well as we continue forward storage class memory. So then the next quick tour of history is scaling over fabrics. So if we look at scaling over fabrics, that journey really started around 2014, even late 2013, as we started to look at, hey, NVMe is great for local, but we can only attach so many PCIe SSDs locally to a system. We really need to be able to attach hundreds and thousands of devices as we move forward. So how do we bring that simplicity and efficiency of NVMe end-to-end and get that capability end-to-end with many queues and many new features and capabilities that everybody wanted to take advantage of? And so what you can see here is kind of an early architectural approach of how do you have the NVMe host software, a host side abstraction, and then underneath it, whether it's PCIe as the transport or RDMA as the transport, or as we've seen TCP being the transport over time, and then you have a controller side transport abstraction. And that's really where we've gotten to. Now, one of the key things we also tried to do was make sure we had took advantage of the commonality between PCI-Express and Fabric. So how do we keep the NVMe specification, how did we leverage 90% of it and only change a few pieces of it? So for example, we had to change, for example, how you enumerate what's present. And so understand those pieces. And for example, instead of doing queues with our commands via memory, we had to go message-based. But how did we leverage those existing pieces? So then if we look at 2016, we had established NVMe over fabrics. We had defined the specification. We had that vision of fiber channel, Rocky, iWarp, next-gen fabrics, all of those pieces, and making sure we didn't have to translate in and out of other fabrics. And so then this shows us as up into the 2016 timeframe and moving into 2017, what the NVMe roadmap really looked like, of taking a look at when we delivered the base specification in 2011, to adding some capabilities that really were meant to address the dual port SSD or dual port HDD type of scenarios with multi-path IO and reservations, into us having more features both for client and for cloud, having that ability to go both ways. And then how did we move into the even further enhancements, and then adding new capabilities like management as well as fabrics. So then lastly, just touching for the last couple minutes on enabling innovation. So on enabling innovation, what we've seen is that NVMe has exploded. And so what we see in both enterprise, cloud, and client, from 2016 to 2021, you can see, for example, in enterprise, we go from 364K units to more than 5,000. You can see in client and cloud, it's also incredibly fast growth rates. So we're just continuing to grow, and it's powering this connected growth in the connected universe as we keep seeing client, cloud, and enterprise. So one of the things that we've been invested in and that you're going to see in the next month or so with NVMe as we keep moving forward is, how do we drive simplicity in a complex world? So we've been doing this work for more than 10 years, and what people can tell you is things just keep getting added and things get more complicated. So for example, we've added zone namespaces, we've added key value capabilities. We're also in the process of adding computational storage capabilities. And so one of the challenges is then, how do we make this understandable for each person as they pick up NVMe as we keep moving forward and keep evolving for the industry? So what we've done is we're trying to make sure that we refactor. So instead of the human glue we've been living with, how do we drive more simplicity in this world of complexity? So what we've done is we've refactored. What you're about to see is NVMe will be introducing NVMe 2.0 shortly. It's a refactored base specification that then cleanly builds out for things like key value or NVMe over fabrics. And we have that common base that's for both fabrics and locally attached storage that everything can build on, but then adding on, are you an enterprise person that cares about a particular feature, or are you a client person that doesn't care about any of that? So how do we make this extensible for the future and keep growing? And so you're going to see, we're going to have specification families, the core, the command sets, and then the transport layers, and then the management interface is a clean modular separate specification. And this 10-year refactoring of what we're doing for NVMe will hopefully allow us to continue to scale and grow for the next 10 years. So lastly, this is what our NVMe roadmap looks like as we keep moving forward. So we're super excited to move into just this NVMe 2.0, the clean refactoring, and get all of your feedback and how do we keep evolving, because I'm so pleased to be part of this journey on storage that my esteemed colleagues have been doing, and how do we just keep evolving as we move forward. So with that, I'll hand it off to Q&A with Tom.
Dal, or you would like to introduce yourself since you were not a presenter?
Sure. I actually went to the first standards meeting on interfaces back in 1977. And the one thing that changed over the period since is that we evolved from taking something that had lots of variation to one. Then it became creating technology so that we could have what we wanted. And we've now moved into the space where the industry groups are creating the technology which the standards are adopting. So we've seen a complete, almost from proprietary back to semi-proprietary over the course of the last 45 years. Very interesting.
Tom, you had a question you wanted to throw out. Tom Coughlin.
Oh, yeah. So my question was, Amber, do you think that eventually we might see NVMe on all the storage devices, including, for instance, hard drives?
Yeah, there's actually work going on with NVMe today on a technical proposal to enable rotating media with NVMe. And that's certainly been a vision for a while there. I think there's finally the impetus really to move it forward in a bigger way. So I think we will see it.
You know, I've got another one if someone else doesn't. Can you guys talk about sort of the social aspect of this? You know, people getting together and starting to do these interfaces. How has that developed over the years? You know, the engineers getting together and creating these specifications.
Well, Tom, I guess we originally did it in standards groups so that there wouldn't be any monopoly issues. And we've evolved from that, where it was a bunch of competitors in a room being a little careful about what they said, but wanting to make progress, to today where competitors actually grow together depending on their adoption of a new technology which improves their performance. So I guess it's a case of you need each other.
You got together because you had to.
Yeah, I think so. I mean, isn't that the way it came along for you, Amber?
That's definitely the way it comes together, because if I'm not working with something that will work for my competition and my customers and the whole ecosystem, it's just not going to go anywhere. So I think that's been super critical, is having the positive collaborative relationships and finding the win-wins for how we move together, right? So it's been critical. And I do see it's been fabulous of the trusted relationships that you get over time of, hey, I know that I'm going to advocate for my company's best interest, but I also have that hat of doing what's best for the industry over time. And I think that the people that care about the industry and how it evolves get involved in standards.
So I think Tom Gardner wanted Brian and I to do the questions. You want to take the first question, Brian, that's up there, and I'll do the second one?
Sure. I actually had a comment that I wanted to make that
sure.
kind of follows along with your question and Dal Elwin's comment. You know, this evolution that you were talking about, Dal, I think, you know, you're saying we're back to proprietary, and yet I think, you know, going along with what Amber was just saying, you could say we're back to proprietary, but it's a proprietary that works for everybody. I mean, it's something that's, you know, not part of, for example,
you
the
nailed
ANSI
it, Brian.
Groups,
that's the
but
big
it is
difference.
certainly beneficial. So I think we really need to.
It's not a lockout.
Yeah, so that's an interesting evolution. I mean, it's sort of like, you know, the competitors are maybe feeling friendlier with each other because they're getting you know, something that can benefit everybody together, and so the competition is maybe not so fierce. Would that even be a way to characterize it?
I think it's self-survival. If you don't cooperate, you wind up with something that is, quote, non-standard. So if you don't work with your competitors to agree on the standard, you wind up in left field, either as a huge winner or a huge loser.
Right. But at the same time, it's interesting that, you know, obviously PCI-Express and NVMe is based on the original, you know, it's based on PCI-Express, which came from PCI, which came from ISIS, so to speak. And so, you know, there's been a whole lot of impact of Intel on all this. So obviously they're a major player. And so they've been creating this foundation that we're all playing with. And so, you know, the fact that we're all using the same PCI-Express bus is itself quite dramatic. And then that came initially from Intel, yet we all play together on that.
Well, look at Cisco and networking. I mean, it's history repeating itself.
Well, and I think there's a tremendous ecosystem lift that we all have to do together. And so how do we work together and make these evolve together? And I think the industry keeps coming together. So so it's really helpful, right?
Most assuredly. So let's see. I think we had a question going back here. Richard Fedek asked, what is the NVMe connection to SNIA? Anybody want to handle that?
So I can start, and others feel free to add in. So one of the things we've been working on with SNIA is management interface work. And so there's a big collaboration with the NVMe management interface, as well as with all the work that SNIA does in that domain. Another key thing we've been working on in the past 2 years is computational storage, and SNIA is leading the way on how to define the use cases, and then how is software connectivity and where do we go? And then if NVMe happens to be the transport, then how is the NVMe organization architecting that connection with what SNIA is driving? So I've seen it as a super positive collaboration. We've even had joint meetings together because so much of the membership overlaps, and just to create that, you know, it's not only collaborating to form a consortia to do a particular standard, but how do our consortias interrelate to get what we need done for the ecosystem and optimize what each of us are really good at.
Okay, there's another question here. It's actually another NVMe question from Hisham El Bakori. I hope I pronounced that right. And I guess maybe this one is maybe for you as well, Amber, right now. Do you follow up on NVMe work in OCP? I think they mean the Open Compute Platform. And of course, I think there's really strong connections. Why don't you go ahead and talk about it, or anybody else would like to talk about that? And OCP in general, which is a very interesting activity.
Yeah, OCP is obviously where a lot of the cloud partners have come together to collaborate. One of the things that the cloud partners that the cloud customers have looked at is how to create effectively profiles that allow them to optimize the features, because one of the challenges with NVMe is we have such a broad feature base that the cloud customers really want to incentivize the SSD vendors to build certain capabilities, right, with that are optimized for cloud. And so how do they provide that input? And certainly one of the things we've been working out is how do we have that cross, for example, a Facebook and a Microsoft and whatnot, they're both on our NVMe board of directors. So how do we cross-pollinate and make sure that we're driving forward together in a cohesive fashion?
Great. Thank you, Amber. We have another question that came in with regard to storage area networks. So there was, some discussion about that, but that really is a whole area that, of course, in many ways is still with us, but it's evolved. Anybody want to take a comment about the evolution of storage area networks amidst all that we've been talking about?
Yeah, I don't mind taking a shot at that. So I did talk really, I didn't actually use the word SAN, but in fact, everything I was talking about was really storage area networks, because I talked about, the fiber channel, which has switches and directors. It's really a way, how do I get block storage, as opposed to file storage, which would be NAS. So, fiber channel is a SAN. I talked about fiber channel. iSCSI is a SAN. I talked about the iSCSI SAN. And really, if I think about it, NVMe over Fabric is nothing but the newest, SAN protocol. That's the way. I don't know if, Amber would agree with that characterization, but to me, it's block storage over the network, shared with switches. In fact, I have an article, I don't know if it's in LinkedIn or Medium or somewhere, that says, SANs are back, and it's really about NVMe or Fabric and stuff like that. To me, it's that's the way I see it anyway. And I'll let others add to that or complement it.
I don't think we use the terms SAN, LAN, or WAN in anybody's presentation. Yeah. And I think I agree with you. Block storage is sort of the contemporaneous term for that, for any of those acronyms. I can answer this next question. The slides will be linked off the Silicon Valley History website, which I gave you at the beginning. And if I get it right, Brian will correct me if I get it wrong. It's www. Brian, why don't you give it?
Sure. SiliconValleyHistory.com. Yeah, I registered that domain about 5 years ago or so. And yep, that's definitely the place we can go to.
Sure. If you go to the events page.
Let's see. So we got.
Go ahead. There's a really interesting thing up here, which I'm going to actually put in chat for everyone.
Go ahead and take that next.
Yeah, I'm going to actually, it's not really a question per se. It's more of an interesting observation. I'm going to put it in chat so everyone can see this. It's Alexander Menon. Again, I'm hoping I pronounced that right. It says, for those not immersed in setting the next generation of standards, the issue of a global issue at a global scale goes back to the 19th century. And there's a reference to Joanne Yates and Craig Murphy, Engineering Rules, Global Standard Setting since 1860. It's a book. And I put it in the chat just so people want to look at it. So let's see. Okay, then there is a question here. How did Sony get pushed out of its own format, for which I'm still looking for an adapter? But I would like to answer that one.
Well, what format?
I'm not sure.
Yeah.
Alexander, would you like to tell us the format?
CD-ROM? I don't know.
Betamax?
Are we talking beta VHS?
VHS beta.
They kind of got creamed on a few formats, didn't they? Oh, well.
Yeah, that's the old idea of, being too proprietary. Like VHS was like for everybody, Sony Betamax is for its own. But yep, of course Sony did get the fact that the famous Supreme Court case with regard to time shifting is based on Betamax. So they did get that notoriety, so to speak. Very, very important thing that we. Well, yeah, but we live with that to this day. It's a very, very important Supreme Court ruling.
I also always find the fascinating thing is it's not necessarily the best technology that wins, right? It's often what can you get people to adopt? Where can you cross the chasm? And often, like if we think about lately, we've had a lot of stuff with open NAND flashing or not open with open channel, right? And whether open channel would be enough, and there have been Denali and other things that people have looked at. And ultimately that, the benefit, there may have been performance benefit, but getting that software in place, getting all of those pieces hasn't really enabled that broad adoption. So that's another thing we just have to continue to always think about is how can people adopt this? Because if it's too complicated for that 5% of performance or 10%, people aren't going to do it.
Well, there's another factor, right? I mean, the Sony question reminds me, I was at IBM there was Token Ring and there was Ethernet. Some of you might remember this stuff.
Yep.
And I thought Token Ring was the better technology, but if you make it too hard for people to get it, or you want, you end up wanting to license it for lots of money, or all of these kinds of factors play into, well, if you want, if that's what you want to do, well, I'll go over here with Ethernet, and that's, this is history, right? So I think that's a good example.
Well, we now know what the question was about. It was about the memory stick.
It was, yes.
Okay.
Sony was pretty good at sticking oddball connectors into cameras and things like that nobody else did. And anytime you get your old Sony camera out, you say, where am I going to find one of those?
I think it was very much a form factor issue, right?
Well, yeah, I think people, design, optimize, and design out as a result the industry standard or the one that's going to be the winner, and that causes lots of problems for them later.
It was competing against things like the SD cards,
So I have a question I'd like to toss out to the rest of you that are, so this is really a question about the influence of the really big hyperscalers on standards and what happens. And, I see some examples of that where, certain standards are emerging that may or may not be widely available to the rest of us. I mean, I think, I don't know if this is a good example, but I'd throw it out. I mean, there's this whole, things that are happening with some of the disk drive form factors where, you go talk to a disk drive vendor and they'll say, well, you can't have that because that's reserved for these two hyperscalers, but, we'll give you the low performance version of that. And I think there's examples of, things in E1.S and E1.L and E3.S and E3.L and, things that maybe, some of the big hyperscalers are driving as an example, but I really didn't want to, I don't really want to focus on that particular one, but in general, the question was about the influence of hyperscalers, how they influence standards. Amber, you're in the middle of all this NVMe stuff. I'm sure there's people, perhaps zone namespaces perhaps came from one of the hyperscalers.
And I did EDSFF, right? For all those form factors. That was, I got to set up that consortium and drive that with Anthony Constantine. So, what I've seen so far is that I think that the hyperscalers have been very useful about how can we do things with simplicity, because I do think that we tend to carry along in an enterprise space some boutique, things of the way we did things versus refactoring and doing it differently. However, I do see that those cloud vendors, right, certainly they have an enormous buying power and can consume what many suppliers can provide. And so, however, can they take us to a better place for how we go together? So I do think that for that broad adoption, the cloud is such a major player that we have to figure out how do we make things that are win-wins? Just like we have to think about the competitive landscape of, I have to make sure that my my competition can win with a standard. How do we think about from cloud and enterprise, what is the subset that will work for both and clients, and then keep evolving, because the cloud will, based on their volumes, cause a lot of evolution. So how do we harness that and use that for good? Because I think it has benefited us in really great ways in several cases.
I have a question for the panel. We've been talking about the cloud. There is so much storage in the cloud. Do we have any kind of a feeling for what percentage of that storage is NVMe and how that's split off? Because I mean, we're talking like, you know, exabytes and more up in the cloud.
Zettabyte. That's, yeah, more than
zettabytes.
Yeah, zettabytes.
Yeah, zettabytes. Yeah. Any idea for the panel? Any percentage or any feeling for how much of it's NVMe, for example?
So, you know, I think most of the storage in the cloud is not high performance storage.
Right.
It's stuff that's sitting in object stores with, you know, S3 interfaces and stuff like that. And, you know, much of it is, you know, either spinning disk or even tape or, you know, I would say 80–90% is of that kind.
Yep.
So it has to be, you know, it has to be less than 10%, because just from the sheer numbers of, you know, where most of the actual data is, it's really not sitting on, you know, very high speed stuff. So that would be my,
and of course,
on that answer.
I think it really comes to, you know, what type of storage are you talking about? When you talk high performance storage, right, which is a smaller subset that Jay's speaking to, then it's an extremely high percentage that people are buying that's NVMe, especially when they're populating. But, you know, how does that evolve over time? And then another thing that I'm seeing is that people are really wanting that end-to-end management. So even though in the back end, it might be a serial ATA or a SCSI or whatever type of drive it is on a hard drive, it may still be from the front, almost an NVMe over Fabrics with the hard drives in the back end that maybe nobody even knows. So, but I completely agree with Jay's comment as well.
Yeah, good point about that. One interesting part of the infrastructure that Facebook has, and perhaps other vendors also, for very low access, like for example, photographs that are 8 or 10 years old, but they become part of a divorce case. You know, Facebook has somehow accessed that data, and they don't want to have somebody go off and, you know, get it for them. It needs to be automatic in some fashion. So a lot of those photos are stored on Blu-ray discs sitting in jukeboxes. And so that, you know, it takes a few minutes to get to the data potentially, but that doesn't matter because you're looking for this one stupid picture from 10 years ago. And how often do you need that? So you need to, in fact, that reminds me, there was a statement that Facebook made when they gave a keynote at Flash Memory Summit approximately 8 years ago. They said they wanted crummy flash.
They did.
The reason they said they wanted crummy flash is they didn't want to pay much for it. And they wanted to have the convenience of flash memory. So that got people thinking, you know, wow, okay, I can relate to that. I mean, you only need to rewrite it once, maybe twice. I can get by with crummy flash.
People don't want to pay more.
Didn't they call it worm, right? Write once, read many, and whatnot. Yeah.
Well, write once, read never. Warn data. So here's a question for Amber with regard to, in fact, we got a few more here. Gosh, we got a bunch of questions now, but one that I thought was important to answer. How about what is going to be the impact of CXL on the storage infrastructures? Because that's a new thing that Intel is pushing right now. So Amber, I'm sure, is the best one to comment about that.
I think that they're very complementary. So, so CXL is, you can think about from a persistent memory and an accelerator use case, where when you're not trying to access it as a storage media and the storage protocols of a block IO, but instead a load store, then CXL is perfect. And so I think the key thing we have to look at is when people are setting up their use cases, they're going to put some really high performance memory, which might be a storage class memory, on CXL for an accelerator. And then they may have the bulk behind NVMe, whether that's a storage class memory, a NAND, or then, you know, have hard drives and whatnot. So I think it's just all part of the tiering journey. And CXL gives you a much better way of, right now, if you look at a Xeon, one of our challenges in servers is how many memory channels can you break out of a socket? Like, for example, we often have 6 to 8 channels of memory. You just start becoming, with a parallel memory interface, very constrained on your number on your ball out and your packages. So CXL is giving us that opportunity to really get that high performance memory, almost in the way you think about NVMe over fabrics, extending NVMe to beyond local. I think about CXL of extending, the parallel memory local further for accelerators.
So, just to add to that answer, the way I see it, just like all hierarchies, we've continually moved. What is the fastest thing in the hierarchy? What's the next fastest, and so on. I think it's not unreasonable to think that disk is the new tape, and flash is the new disk, and persistent memory, whether it's CXL attached or otherwise, is the new flash, right? I mean, I think this continues to evolve, and so I think watch this space. I would say, Amber, I don't really know what's going on with Micron and you guys and Optane and all this stuff, but I've always been a fan of that layer in that hierarchy, and hopefully there'll be other players, and hopefully putting it on CXL makes it more open so others can have their technologies for persistent memory attached to the CXL bus. I really do think that there's a shifting, the shifting I'm talking about with disk as the new tape and flash as the new disk and persistent memory as the new flash, right? That I think will happen in my mind.
So there's a question here that I'm from Michael McDonald, and I'm going to kind of draft off of it in a sense. He was asking about, will Google and AWS develop their own in-house interfaces and protocols optimized around their environment use cases rather than use standards? And I guess my shift of that is, are all of the the hyperscale guys playing together here? Do we really have a level playing field, or they're all buying into these standards?
If you look at AWS, right? Annapurna Labs was purchased by Amazon AWS a few years ago, or maybe moving more towards 5 to 7 now. And Annapurna was actually one of the early contributors to NVMe-Express and actually NVMe over fabrics. And so now how much AWS's infrastructure, if you look at the literature on Nitro that's out there, how much of it is exactly NVMe over fabrics, but it is heavily derived, and AWS utilizes that in their infrastructure. If we think about Google, those of us that have worked with Google for a long time, they've done at times gone their own path. They've got a ton of expertise, and I see Google participants show up at JEDEC, at NVMe, all these places. So I think it's all going to be about for these different cloud providers. I think it's all a case of when does the economic balance mean that they're going to get better KPIs and a better return on investment of doing their own versus leveraging the ecosystem. And I think now that we're much broader, I think that they continue to come along. But I see a lot of great partnership between the various cloud vendors, and it'll keep being a dynamic space.
But I see, having worked with the hyperscalers for several years, I mean, there is a fair amount of stuff that's fairly unique to what they do. I mean, because they own everything end to end, the OS, the driver, the hypervisor, down to all the way down, that where it benefits them, they will do things that are unique. But I agree with you, Amber. I do see that as things like NVMe and NVMe over Fabric, not everybody's on NVMe over Fabric, but I see more and more of, either that or very similar ideas, like you've introduced queue pairs and queuing, and okay, we know queue pairs is a good idea, so we're going to do something that's almost NVMe over Fabric, even if it's not identical. Anyway, that's
I think many organizations fail to discern the difference between we can do that and should we do that.
Yeah.
There's also another important factor here with regard to Facebook's Open Compute project. And that's really analogous to this idea of companies beginning to call their own shots. Well, Facebook consumes so much storage and so much compute that they can, help define what they really want and have people follow and implement it for them. It's like if you look at some of their, a lot of their data centers, or like 80-story tall buildings on their side that get filled from front to back with compute and storage, and then you put one right next to it, fill it from front to back once again. So they are consuming like mad, so they can really call the shots with the Open Compute project.
Although they... Sorry, go ahead, Tom.
Oh no, I was just going to say, except that they also are working together with other people, so they are influencing it. That's for sure. But
exactly, they're working with others and helping. Economy of scale is helping them and helping everybody else as well.
Exactly. Brian, do you want to ask the security one, or you want me to do that one?
Well, you know what? There's something I really wanted to bring up that wasn't stated directly, but it's a really important thing that maybe not everybody fully appreciates. But a big thing that NVMe brought to us is getting rid of this stupid abstraction that we've lived with for so long, in which the storage was separate from the compute. So NVMe brings that directly in, so you can directly access with microprocessor instructions the storage, and not worry about this open, close, read, write, old infrastructure that we've always had for external devices, because now we bring them so close we can access them just like memory. So that's something that's really important. That's these numbers that we're looking at, those are so incredible, are made possible in large part by the fact that we no longer have that infrastructure in the way. So you want to go ahead and ask that question, Tom?
Go ahead.
I think you just did.
I think you answered it, or you tried to answer it.
Well, I'll ask.
Did I actually answer that? I was actually bringing up a point that I wanted on my own.
Oh, I thought you were actually asking.
Go ahead.
Well, here's a question. It's from Alexander Menon.
I was asking and answering my own question.
You were, in fact. maybe your turn is gone then. So, given the trend of crypto crime, what's the place in maintaining security between the cloud and local memories? And I think this brings up a really interesting point. Security and memory, especially when potentially, everything's connected together. Could you talk about that? Oh, there's a pause.
Blank.
Okay.
Well, there's companies that are certainly addressing that, like Rubrik is one of those companies.
Oh, there are, yeah. Is there anything in the
anyway, there's
Go ahead.
Yeah, so there's companies out there. For example, when I read about the cybercrime, like with regard to the pipeline on the East Coast, getting hacked and all. So companies are definitely creating that security within the cloud, so that whatever data you've got, they are encrypting it and protecting it for you in the cloud, so that these kinds of situations don't need to happen. So there's a lot of people out there who are providing this solution, and so a lot of people are learning the hard way, having to pay millions of dollars when their data gets hijacked.
Oh, and the other thing is encrypting things, all the time, so that nothing's ever in the clear. So
and one of the key things we have to look at is if you take a look at, for example, the Trusted Computing Group, NVMe continues to collaborate with them closely, and one of the things we're working on is something called key per IO. And so the concept is, do you have a key per IO that goes to the device? Because one of the challenges we have is, if you look at self-encrypting drives, right, it was one key. And if we've got many tenants that are sharing data all on one drive, that really doesn't help us. So how do you get to where you can have 64 keys, 128 keys, this multi-key encryption capability where you can pass along the key with the data and make sure, or do that negotiation effectively to keep it all secure, and make sure you're saying, hey, utilize key number 3 with this one that I've already negotiated in a secure fashion. So that's really where we have to head, is making sure that we can continue to enable where we have multi-tenant capability on all of our devices, because everything is shared to get that. Nobody wants dark storage, because dark flash or dark storage class memory, it's so expensive. And so that's where we just have to keep optimizing and being able to let multiple tenants share, and security is a critical piece of that.
So the other directions here are, security obviously is very, very expensive. And I know Intel is doing things to bring down the cost of doing crypto, but, there are these new DPUs and other forms of smart NICs that offload that kind of work into other kinds of ASICs, so you can encrypt data very close to as it leaves the server, and then it's encrypted entirely on the network, even within the data center. These days, for example, if you buy a storage box and even if it's within a data center, if the encryption only happens in the storage box, sometimes customers will say, well, that's not good enough for me. I need the encryption to begin all the way at the server end, and then and move it encrypted over the wires. The company I work for is building something called a DPU that does all this encryption at terabits per second, completely line rate. And the DPU has a secure enclave in it. So like Amber was talking about, you can store multiple keys and have that all be protected. And these cards will ensure that, when your server boots up, bad stuff isn't, it's not bad stuff that's booting up. So there's a lot of stuff that's happening and needs to happen, because I think that the threat from security is just rising. It's just rising, and we continue to need to deal with it.
And let's not even thinking about quantum, right? It's going to keep getting more and more complicated, right? So it'll keep us all in jobs, right?
It sure will.
It's been a interesting and informative session. I'd like to thank all the panelists for their viewpoints and the time they took to prepare the presentations. The slides will be available at our website, www.siliconvalleyhistory.com.